Good day, everyone. We are going to solve this propped cantilever beam with trapezoidal load as shown in the figure. We are going to solve for moment at A, the vertical reaction at A, and the simple reaction at B. Let us start. Of course, we can actually model this solution for this particular situation. We can solve for RB first. Let us forget first the MA and RA. So we're going to start with the solution for RB. Then we are going to model our solution with this situation, a concentrated load on the prop beam. The reaction actually at the simple support is given by this formula. The RB is equal to PA squared all over 2L cubed times 3L minus A, where A and L are these dimensions. So to apply this formula to our situation for trapezoidal loading, we're going to establish our coordinate axis. Let us take this point as our origin. So that this is our XY plane. Now, let us create a strip, and that strip will serve as our P. Okay? That P here in the figure. Now, the dimensions of this strip, of course, is y dx. That is the differential with dx. So that the value of P will become the area of this rectangular strip, y times dx. And we are going to call the distance from the origin to the value of P as x. That will serve as our A in our formula. Now, let us model the equation of this line in the xy plane. Let us create the equation of that line. We can use the formula y minus y1 in our analytic geometry is equal to mx minus x1. Okay, let us take this point as our point 1. The coordinates of this point is actually 2 meters. The x is 2 meters. The y is 4 kilonewton per meter. So this is y minus y1 is equal to m. The slope of this line is y sub 2. That it will become 12 minus y sub 1. That is equal to 4. X sub 2, this point actually has coordinates 5, 12. Okay, 5, 12. And this one is, let me write that one, 2, 4. Okay, x minus x1, x sub 2 is 5, minus x1 is 2, x minus x1 is 2. So therefore, our equation will become y minus y is equal to, this is 12 minus 4 is 8 all over 3 x minus 2 transpose the negative 4. This will become plus 4. So our y will become 8 over 3 of x. We have this 16 over 3 negative plus 4. Negative 16 over 3 plus 4. What is that? We have this 12 minus 16, that is equal to negative 4. Negative 4/3. That will be our equation for y. Now, to apply this equation, to apply this formula for RB, we can use integration. So the RB now will become, let me write this first, 2L cubed, 1 over 2 times 6 cube. Our span is 6, 2, 3, 1, 6 cube. Then P, our P is this one, y dx. Okay, that will be our value of P. Let me write it here. This is 512. So the value of P is equal to y is 8 over 3 of x minus 4/3. That is the value of P dx. That is y dx. So we have this equation, PA squared. Our P is 8 over 3 of x, 8 over 3 of x minus 4/3 dx. Okay, dx. 3L minus 6. 3 times L, actually 3 times 6 is 18. 18 minus x. Okay? Then sum up, which means we are going to integrate. With limits, it starts from 2 up to 5. Okay? From 2 to 5. This is our answer for RB. So let us integrate this one. This is the answer for RB. Let's go to our Canon calculator or Casio calculator. Sorry for that. We have this, the Casio calculator, my favorite calculator actually. We have this 8 over 3. Let's first write the parentheses. 8 over 3 alpha x minus 4 thirds. Minus 4 thirds times 18. I forget the a squared. I forget this one. This portion here. So, may I erase this first? Erase. We have this P. Change the color. P dx of a squared. We have this x squared. 3L. 3 times 6, that is 18 minus x. That is our quantity to integrate. 3 times 6. Okay. That is 3L minus x. Let's go back to our calculator. We have this alpha x. Okay. Alpha x raised to 2. What happened? Alpha x, not shift x. Alpha x raised to 2. Okay. Then 18 minus alpha x. Limits from 2 to 5. Of course, we did not include yet the of 1 over 2L cube. So, this is our answer for integration. 8 alpha x squared, may I check? We have this 2 from 2 to 5 minus 4 thirds, okay. Correct. 18 minus alpha x. All right. The answer is that one divided by 2 times 6 cube. 6 cube. Okay. So 8209 over 720 in decimal, that is 11.4. This is 11.4 kilonewton. That is our answer for RB. With RB known, we cannot solve for MA and RA because we already have the value of RB. Let us erase this one. That's the value of P. So, what is the value of RB? Of course, summation of forces in the vertical direction, 0. Summation of forces in the vertical direction is equal to 0. We have RA plus RB. Okay? RA plus RB is equal to the area of this trapezoid. The area of the trapezoid, may I erase this one? We don't need this anymore. RA plus RB is the area of the trapezoid, 1/2. 4 plus 12 times 3. Therefore, RA is equal to, what is this value? 16 divided by 2 is 24. 24 minus RB is 11.4. So, this is our answer for RA. How much is this one? Okay. Move the calculator here. 24 minus 11.4 is equal to 12.6. 12.6 kilonewton. And that is our answer for RA, 12.6. Then, how about the moment at A? The moment at A. Summation of moment at A is equal to 0. That is the moment at A. No, not equal to 0. We're going to solve that one. Summation of moment at A. That is the total moment at A. The moment at A, of course, is equal to, number 1 is due to RB. That is 6 RB. 6 times RB. Minus, let us, because we don't know that the centroid, we don't have a direct formula for the centroid of a trapezoid. If you have a direct formula for that, you can use that. But I will only use the centroid of the triangle. So we have these two triangles. This first triangle, the area is here, the centroid is here. The second triangle, the centroid is approximately here. Okay. So those are approximate locations. This is actually 3 meters. 3 meters. Well, this one is 4 meters. Okay. Approximating the drawing. We have this 1/2 for the first triangle. Base is 3. Altitude is 4. The moment arm is 3. Minus 1/2. The base is 3. Altitude is 12. The moment arm is 4. So this is our moment at A, and this is our answer. Let's do the calculator. We have this 6 times RB. 6 times 11.4 minus 9 times 2. 9 times 2 minus 3 times 6. 3 times 6. That is 6 times 12. 6 times 12. That is negative 21.6. Negative 21.6 kilonewton meter, and that is our answer for the moment at A. Okay? That's it. But of course, this is not the purpose of this video, because according to our title, the solution that we are going to present here is the moment distribution method. So if you have the direct formula for this one, you can actually use this formula. But we are going to solve this by moment distribution method. It will also involve integration. That's why I presented this solution with the direct formula. All right. So for the moment distribution method, we are going to lock first this two ends. So our both ends will become our beam will become a fixed-ended beam. Okay. For that fixed-ended beam, we are going to solve the fixed end moments. So we're going to have this formula for the fixed end moment at A. This is actually PAB squared all over L squared. That is negative. That is our assumption. Our assumption for moment distribution method, the counterclockwise reaction is negative. The clockwise reaction, this is positive. This value is PA squared B all over L squared. Notice the powers of A and B. The changed powers. Okay, the A becomes A squared here. The B squared here becomes B raised to 1 in here. Okay. Again, our assumption is counterclockwise negative, clockwise positive. That is only an assumption, which means that we need to be consistent up to the point of interpretation for these assumptions of the rotation of our angle. Now, we are going to model this for the fixed end moment in our actual beam. We are going to model this equation with a strip again. So we are going to select the coordinates of our XY plane. This is our origin. Now, create again a strip with area ydx, and that will serve as our P ydx. And this is the distance A and B. So this is the distance A, and this is the distance B. With our L, again, equal to 6 meters. This is the value of L. Okay? 6 meters. Now, what is our fixed end moment AB? Fixed end moment AB. That is from A to B. That will be P. Negative P. Our P is from our previous... We have the same value of P from our previous solution. That is 8 over 3 of x minus 4/3, because we have the same coordinate axis. All right? So 8 over 3 of x minus 4/3. P is 8 over 3 of x. May I write this first? 1 over 6 squared. Okay? 8 over 3 of x minus 4/3 times x times b. 6 minus x raised to 2. Sum up, which means we're going to integrate. Limits from 2 to 5 again. From 2 to 5. That is our fixed end moment at a and b. Let us do the calculator again. Okay. Casio calculator. We have this one. Integral 8 over 3 of alpha x minus 4/3. Minus 4/3. What happened? Minus 4/3 times alpha x times 6 minus alpha x. Alpha x raised to 2. Okay? Limits from 2 to 5. From 2 to 5, that is our solution, divided by 36. 36, so 731 over 60. That is 12.18. It's actually negative 12.18. Negative 12.18. Take note that for fixed end moment AB, we don't need to rewrite we don't need to write our integral equation BA for the fixed end moment BA because we simply switch the power of A and B. So this X, this represents A, this will become raised to 2, and this will become raised to 1. So let us go directly to our calculator. We have this replay your calculator, then edit the powers of x and 6 minus x. So this will become raised to 2. And the power of 6 minus x will become 1. That's it. Close parenthesis. That is our answer. Divided by 36 again. That is 6 squared. Okay. 1129 over 60. And that is 18.82. 18.82. Kilonewton meter. Let us do the tabulation to solve for RB. Let us tabulate our results. For the moment distribution method, we have this beam stiffness. The next is the distribution factor, and the next is the fixed end moments. So we have this tabulation. Okay. We only have one span, so our K is the beam stiffness is 1. Okay, this is the A and this is the B. The beam stiffness is 1. We have this A and B. For the whole beam, the distribution factor here is, for the original beam is, this is a fixed end, this is actually 0, and here is 100%. Okay, the distribution factor. The fixed end moment is negative 12.18. The value here is 18.82. That's it. Then release all the locks. We lock all the supports or all the joints. We have these fixed-ended beams. Now, if we really fixed-ended beam, if we release all the locks, we go back to the original support. Let us erase this one. We will go back to the original support, and let us solve for. We are going actually to solve for the moment. For the moment, okay, the moment at A. Now, if we release the original support, we are going to distribute this one. Let us going to balance the moment here because we know that the simple support has no moment. It cannot prevent a moment. We have this negative 18.82. And 100% of this one will go to this support will pass this unbalanced moment to the left support. And what will happen here? Half of it will go to MA, the moment at A. So half of 18.82. 18.82 divided by 2. That is 9.41. Negative 9.41. And there is no more unbalanced moment. There is sum up. That's it. That's the beauty of the moment integration and the moment distribution method, because we only have to do one distribution and we are done with the solution. So sum up, negative 12.18 plus negative 9.41. $12.18 plus 9.41. That is 21.59. Then here is 0. So the moment at A, this is our answer, the moment at A. Negative 21.59. And we can check that in our previous solution. Negative 21.59 if we are correct. Okay. In our previous solution, we have this negative 21.6. There's a difference in what is that? Decimal 21.6. How about the reactions? The reactions. Where are you? I pressed the wrong button here. 21.6, that is, they are correct. They are the same. 21.6 if we are going to round off this one. Then how about the reactions at A and B? So we can solve now the reactions at A and B if we already have the moment. So for the reaction at B first, of course, summation of moment at A. Summation of moment, we are going to use summation of moment at A. This is not 0. This is negative 21.59. We can solve for RB because RA cannot produce a moment at A. This force cannot contribute to the moment at A. Only the RB. Okay? Let's erase this one. We have this 6RB minus this triangle. 1/2. Base is 3. Altitude is 4. The moment arm is 3. That is the distance of the centroid of this triangle from point A. Minus this triangle. Okay, 1/2. Base is 3. Altitude is 12. The moment arm is 4. And this is equal to negative 21.6. Let's say this is 21.6. Okay. 21.6. That's it. What is the value of RB? Calculator again. Casio calculator. May I move this one? Hey, what happened? Negative 21.6 plus 0.5. Let us calculate this first. Okay. 0.5 times 3 times 12 times 4 plus 0.5 times 3 times 4 times 3. Okay? Divided by 6. This is our answer. 57 over 5, 11.4. 11.4 kilonewton, and that is our answer. How about the RA? Of course, we are going to use summation of forces in the vertical direction. Summation of forces in the vertical direction is equal to 0. We can now solve for the value of RA. That will be RA plus RB, which is equal to 11.4, is equal to the area of the trapezoid. 1/2 4 plus 12 times 3. And this is our answer. Okay? Calculator again. 11.4 minus 1.5 times 16. Of course, we are going to take the positive value. 12.6. 12.6 kilonewton, and this is our answer. Now, let us understand the why. Why I discuss this one? Because it is like the almost the same approach, because we do integration for the reaction and for the fixed end moments. If we are going to recall our first solution, we do the integration here. Then we do this integration using this formula, and we need to memorize this formula if we want to use this approach. And we also do the integration here. Okay? And we need to write this formula also. We need to memorize this formula also if we are going to use this approach. But why the title is about the moment distribution method and not the other one? The idea is you will use mostly the fixed end moments, the fixed end moment formula in comparison, or in if you are going to compare the two. The most widely used is this fixed end moments, not the other one, not this one. We will seldom use this formula. Okay, may I erase this one? We only need this formula if we are going to use this directly to the prop beam to solve for the moment reaction at the simple support. But for any other occasion, we are not going to use this formula anymore. Okay? Whereas for this formula, we will use this in, of course, the fixed end moments, the usual fixed end moments, the moment distribution method, and the other method. There are many methods that utilize these fixed end moments. So I highly suggest that you are going to master these two formulas. The PA squared B at the right, and the PAB squared at the left of the fixed-ended beam. I hope you get what I mean, although I cannot deliver it in words eloquently, with the right words. But anyway, hopefully you learned something from this video. Thank you for watching. Bye-bye.